Winter, 1885. The coastal forests of Washington Territory stretched unbroken for hundreds of miles. Douglas fir, Sitka spruce, and western red cedar rising 200 feet into perpetual mist. These weren't trees. They were living monuments, some over 1,000 years old, their trunks 15 feet across, their weight measured in tens of thousands of pounds. And men were trying to move them, by hand, with axes, crosscut saws, and teams of exhausted oxen. Logging crews inched through terrain so steep that standing upright required holding on to bark. A single tree could take a week to fall, another month to drag half a mile. Dozens died every year, crushed under rolling logs, caught in snapping cables, buried in mudslides triggered by their own work. The industry was choking on its own ambition. Then, from a small mill in Humboldt County, California, came a machine so dangerous, so loud, and so powerful that veteran loggers refused to work near it. A 10-ton iron boiler mounted on wooden skids. A single steam-powered drum wrapped in a mile of steel cable. No wheels, no tracks, just raw, brutal mechanical advantage. They called it the steam donkey, and it changed everything. If you're watching from anywhere in the world where forests were cut, railroads were built, or progress came at the cost of human limits, drop a comment and tell us where you're from. Hit subscribe, because we're about to show you the machine that made the impossible routine. And if you think modern engineering is always better than what came before, stick around. You might change your mind. Before steam entered the forest, logging was a war of attrition fought with muscle, patience, and blood. A logging crew in the 1870s Pacific Northwest worked like this. First fallers, men with 12-foot crosscut saws, spent days cutting notches into a tree's base, standing on springboards jammed into the trunk 10 feet off the ground just to reach where that wasn't rotted or filled with pitch. The saw itself weighed 30 pounds. Two men pulled it back and forth, for 8 to 10 hours, until their hands bled through gloves and the tree finally cracked, groaned, and fell, usually in the wrong direction. Once down, the tree became a different problem. A single Douglas fir log, 20 feet long and 6 feet thick, weighed 15 to 20 tons. There were no roads, no railroads, just mud, roots, and slopes that could break an ankle in seconds. Ox teams, sometimes 12 to 16 animals chained together, dragged logs using iron hooks and thick hemp ropes. In dry weather, they moved maybe 200 feet per hour. In rain, which was constant, the oxen sank to their knees. Logs rolled sideways, snapping chains, crushing animals, killing men who couldn't get out of the way fast enough. On steep grades, a runaway log could slide a quarter mile, obliterating everything in its path. The math was unforgiving. A good crew could move 5 logs a day. Maybe a mill 10 miles away needed 200 logs a day to stay profitable. The industry was trapped. Limitless timber, bottomless demand, and no way to connect the two. Manual logging wasn't just slow. It was a death sentence stretched over years, measured in hernias, amputations, and unmarked graves on muddy hillsides. Something had to break. The economic reality was equally brutal. A logging operation in the 1870s required massive capital investment just to achieve marginal output. Teams of 20 to 30 men, working 6 days a week in conditions that destroyed bodies within a decade, could harvest perhaps 30 to 40 logs per week from accessible terrain. But accessible terrain ran out fast. The best timber, the massive old-growth giants that mills craved, stood on slopes so steep that ox teams simply refused to climb them. Camp operators tried everything. They built primitive log skid roads, parallel logs laid perpendicular to haul direction, greased with oil or animal fat, that required constant maintenance and still broke apart under the weight. They attempted splash dams, flooding valleys to float logs downstream, but this worked only in specific terrain and destroyed the log's value through impact damage. Some operations use elaborate systems of wooden rails and horse-drawn carts, but these required crews to build infrastructure faster than they cut timber, a losing proposition in every sense. The human cost compounded daily. A choker setter crushed by a rolling log left a widow and children with no compensation, no pension, no recourse. Company records from the era, what few survive, list injuries with coal deficiency. Lost 3 fingers to cable snap, March 14th. Buried under slash pile, no recovery possible. Trampled by spooked ox team, died on site. Insurance didn't exist for this work. The job paid well by the standards of time, $2 to $3 per day for skill fallers, because everyone knew the odds. Yet demand kept rising. The Transcontinental Railroad, completed in 1869, opened Western timber to Eastern markets. San Francisco was rebuilding after fires. Mines needed support timbers. The country was industrializing, and was a feedstock for everything: homes, ships, rail ties, furniture, fuel. The Pacific Northwest held an estimated 600 billion board feet of standing timber, enough to build the entire nation 3 times over. But it might as well have been on the moon, because no one could move it fast enough to matter. The man who broke it wasn't a logger. He was a millwright. John Dalbier ran a sawmill in Eureka, California, in the heart of Humboldt County's Redwood Empire. By 1881, he watched too many oxen collapse, too many men crippled, and too much timber left rotting on hillsides because no one could move it. He knew steam engines. He'd seen them power mills, riverboats, and mining hoists. The question wasn't whether steam could pull a log. It was whether anyone would let it. Dalbier's first prototype was deceptively simple: a vertical fire tube boiler, about 6 feet tall, mounted on a heavy wooden sled. Attached to the boiler was a single-cylinder steam engine, no bigger than a whiskey barrel, connected to a horizontal drum. Wrapped around that drum was 1,000 feet of braided steel cable, 3/4 of an inch thick. The entire machine weighed roughly 8 tons and could be dragged into position by a team of horses. The principle was old, mechanical advantage through pulleys and leverage, but the execution was new. At 120 psi of steam pressure, the engine could rotate the drum with enough force to generate 20 tons of pulling power at the cable. In theory, one man with firebox and a lever could outpull 40 oxen. In practice, no one believed him. When Dalbier hauled the machine to a logging site outside Eureka in late 1881, the reaction ranged from skepticism to outright hostility. Veteran loggers called it a death trap. That boiler will blow and kill half the crew. Cable that thin will snap and cut a man in half. You can't control steam like you control animals. Dalbier fired up the boiler. Black smoke poured from the stack. The engine hissed and clanked. He signaled the rigging crew to attach the cable to a 12-ton redwood log lying 800 feet uphill, mired in mud that had swallowed 2 ox teams a week before. He pulled the throttle. The drum turned. The cable went tight. The log moved, not slowly, not with hesitation. It moved like it had been waiting. Mud sprayed. The cable sang under tension. In 6 minutes, the log was at the landing, and John Dalbier had just made every ox in California obsolete. The loggers stood silent. Then one of the older hook tenders walked up to the machine, studied the cable still vibrating with residual tension, and looked back at the furrow the log had carved through 800 feet of mud and slash. He spat tobacco juice on the ground and said, "Do it again." Dalbier did. 8 more logs that afternoon, each one bigger than the last, each one pulled from positions the oxen couldn't reach. By sunset, the crew had moved more timber than they'd averaged in a week. The cost: 40 pounds of firewood, 20 gallons of water, and one man's attention. No animals to feed, no chains to repair, no bodies to bury. Word spread fast. Within 6 months, Dalbier had sold 12 machines to operations throughout Humboldt and Mendocino counties. By 1883, the Dalbier and Carson Lumber Company was manufacturing steam donkeys as fast as their San Francisco foundry could cast parts. Other companies jumped in: Washington Iron Works, Willamette Iron and Steel, each adding refinements: larger boilers, dual drums for haulback systems, improved brake designs, portability features for moving between logging sites. But adoption wasn't universal, and resistance came from unexpected places. Established logging operations had invested heavily in ox teams, skid roads, and trained bull hackers, men who'd spent careers mastering the art of animal-powered logging. Switching to steam meant writing off that capital and retraining crews in an entirely new skill set. Some camp bosses argued, with justification, that the steam donkey was too dangerous, too expensive to repair, too dependent on fuel supplies in remote areas where firewood was abundant, but coal had to be hauled in at great cost. The machine's early reputation for danger wasn't unfounded. Boiler explosions did happen, usually from operator error, running the water level too low, overpressurizing the system, or using a boiler with corroded tubes. Cable failures were common in the first years, before manufacturers standardized on high-carbon steel wire rope, and before operators learned to inspect for wear. A snap cable under 15 tons of tension didn't just break. It whipped through the air at speeds that could decapitate. Period newspapers carried accounts of steam donkey tragedies with enough regularity that insurance underwriters initially refused to cover the machines. The steam donkey wasn't elegant. It was a solution built for survival, not precision, a machine designed to work in places where nothing else could. At its core sat a vertical fire tube boiler, typically 4 to 5 feet in diameter and 6 to 8 feet tall, constructed from riveted steel plates half an inch thick. Inside, dozens of steel tubes carried heat from a firebox at the base up through 50 to 80 gallons of water, generating steam at 100 to 150 pounds per square inch. That steam fed directly into a single-cylinder or double-cylinder engine mounted beside the boiler. Simple, heavy, and nearly impossible to break. The engine's piston drove a horizontal drum, 3 to 4 feet wide, capable of holding up to 2,000 feet of steel cable. The cable itself, 3/4 of an inch to 1 1/4 inches in diameter, was a machine's real power. Wrapped under tension and controlled by a friction brake, it could pull with forces exceeding 30 tons when rigged through a system of blocks and pulleys. Before we go further, if you're getting value from this, hit that subscribe button. We're covering machines that textbooks forgot, and there's a lot more coming. Drop a comment. Have you ever worked with cable systems, old steam equipment, or anything that could crush you if you made one wrong move? Let's hear it. Here's how it worked in the field. Riggers ran the main line, the primary pulling cable, from the donkey's drum out to a large tree or anchor point, sometimes over 1,000 feet away. From there, the cable looped through a heavy steel block and returned to attach to the log. This created a 2-to-1 mechanical advantage. The donkey pulled with 15 tons of force, but the log felt 30 tons. For longer distances or complex terrain, crews added a haulback line, a lighter cable that returned the main line to the woods after each pull, and sometimes a skyline, an elevated cable strung between 2 spar trees that lifted logs off the ground entirely, letting them fly over stumps, ravines, and slash piles like they weighed nothing. The donkey puncher, the operator, controlled everything from a single position, one lever for the throttle, one for the brake. No gauges, no safety cutoffs, just steam pressure, cable tension, and experience. A good donkey puncher could feel a snag in a line before it became a disaster. A bad one killed people. The machine weighed 8 to 12 tons depending on the model, but it wasn't built to move itself. It sat on wooden skids and was hauled into position by horse teams or, later, by its own cable, winching itself forward like a mechanical inchworm. Setup took hours. Breakdown took minutes if something failed. And things failed constantly. Steam donkeys operated in conditions no engineer would design for. Boilers were fed with whatever burned, scrap lumber, bark, greenwood, even coal when available, and the quality of fuel determined everything. Low grade would produce inconsistent heat, causing pressure fluctuations that made smooth operation nearly impossible. High resin wood, common in pine and fir logging, created creosote buildup in the fire tubes, reducing efficiency and increasing the risk of blockage. Operators learned to blow down the boiler daily, venting steam and water under pressure to clear sediment, a procedure that wasted fuel but prevented catastrophic tube failures. The cable system required constant vigilance. Steel wire rope in the 1880s wasn't the refined product we know today. It was hand-spliced, irregularly twisted, and prone to developing fish hooks, broken wire strands that protruded from the cable's surface and could tear through leather gloves or flesh with equal ease. A cable under working load stretched, heated up from friction, and wore unevenly depending on how it passed through blocks and over rough terrain. Experienced riggers inspected cable daily, looking for kinks, fraying, or the telltale bird caging pattern that indicated internal wire breakage. A compromised cable wasn't repaired. It was cut out and the ends respliced, reducing the system's total length until the cable was eventually retired. Mechanical advantage was the steam donkey's greatest asset and its most misunderstood feature. The basic principle, using pulleys to multiply force, was ancient, but applying in a logging show required improvisation bordering on art. A straight pull from donkey to log generated the drum's raw power, perhaps 12 to 15 tons. Running that cable through a single fixed block doubled the force to 24 to 30 tons. Adding a second moving block could theoretically quadruple it. But each pulley introduced friction losses, and the system's geometry became exponentially more complex. In practice, veteran hook tenders developed rule-of-thumb methods. For uphill pulls on grades steeper than 30%, use a 3-part line with 2 blocks and accept a slower line speed. For long horizontal drags across flat ground, a straight pull moved faster even if it couldn't handle the heaviest logs. For logs hung up on stumps or buried in slash, use a running block, a lightweight pulley attached directly to the log that allowed the cable pull from multiple angles in sequence, walking the log free rather than trying to overpower the obstruction. None of this appeared in manufacturer manuals. It was field knowledge, learned through trial, error, and enough destroyed equipment to bankrupt smaller operations. Operating a steam donkey wasn't a job. It was a coordinated act of controlled chaos involving a dozen men, any one of whom could die if the rhythm broke. At the center was the donkey puncher, the engineer who ran the machine. He stood or sat on a small platform bolted to the sled, one hand on the throttle lever, one on the friction brake, eyes locked on the cable and the forest beyond. The donkey puncher didn't see the logs being yarded. He relied entirely on signals, whistle blasts sent through a steam-powered horn that could be heard for miles. Those signals came from the whistle punk, usually the youngest or newest member of the crew, stationed somewhere between the donkey and the rigging site. He operated a wire connected to the donkey's whistle and transmitted commands using a simple code. 1 blast, start pulling. 2 blasts, stop. 3 blasts, slacken the line. Rapid bursts, emergency, stop everything. The whistle punk didn't decide when to signal. He watched the choker setters and hook tenders working in the forest and relayed their hand signals back to the donkey. If he missed a signal or sent the wrong one, men died. Out in the woods, the choker setters did the most dangerous work. They ran into freshly cut timber, climbed over slash piles, and wrapped heavy steel chokers, short cables with sliding nooses, around logs that weighed 10 to 40 tons. Once the choker was set, they scrambled out of the way, signaled the whistle punk, and prayed the log didn't roll, spin, or snag on the way in. The hook tender supervised the rigging crew and positioned the blocks and cables. A veteran hook tender understood physics without math. He knew how angles, tension, and terrain interacted, and he knew that a cable under 20 tons of load would cut a man in half if it snapped. Back at the donkey, the firemen fed the boiler. Wood, bark, and slash burned constantly. Water levels had to be monitored visually through a glass gauge. Too little water, and the boiler could rupture. Too much, and the steam pressure dropped, leaving a 30-ton log halfway up a muddy slope with rigging crew pinned below it. The noise was relentless. Steam hissed from relief valves. The engine clanked with each stroke. The cable screeched through blocks and across bark. Men shouted, but the machine drowned them out. Communication was visual and mechanical, hand signals, whistle codes, and the shared understanding that hesitation equaled injury. Shifts ran 10 to 12 hours, sometimes longer if the weather cleared or a quota had to be met. The heat from the firebox was suffocating in summer, a brief comfort in winter. The air smelled like coal smoke, hot steel, and pine sap burned into metal. At the end of the shift, every man's hands were raw. His hearing was shot, and his bones ached from a vibration of steel under constant strain. And the next morning, they did it again. The dangers multiplied in ways that became apparent only through experience. A cable pulling a log uphill generated enormous lateral force if the log shifted even slightly offline. If the log rolled, the cable could swing 20 or 30 feet sideways in a fraction of a second, clearing everything in its path, trees, stumps, men. Choker setters learned to work from the uphill side when possible and to never, ever stand directly in line with a cable under tension. The rule was simple. If you can see the cable vibrating, you're too close. Weather turned everything unpredictable. Rain, and there was always rain in the Pacific Northwest, made logs slick, slopes unstable, and footing treacherous. A log that weighed 20 tons dry could absorb another 2 or 3 tons of water, pushing the system past its rated capacity without warning. Mud changed the coefficient of friction unpredictably. A log might slide freely one moment and hang up completely the next, causing the cable to go slack and then snap tight with shock load that could shear a block's mounting pin or strip the drum's brake lining. Cold introduced different problems. Below 20 degrees Fahrenheit, about -7 degrees Celsius, steel became brittle. Cables that flexed normally in warm weather could crack internally when cold, developing hidden fractures that propagated until the cable failed without warning. Boiler water froze overnight if the fire wasn't maintained, and restarting a coal boiler in freezing conditions took hours of careful heating to prevent thermal shock from cracking the cast iron components. Crews working winter shows, operations that ran through snow and ice, learned to keep the donkey running 24 hours, with a night fireman whose only job was feeding the firebox and monitoring water levels. The psychological toll was harder to quantify, but no less real. Every man on a steam donkey crew had seen accidents. Some had caused them: a misjudged signal, a choker set on rotten wood, a brake released too fast. The knowledge that a single mistake could kill someone, maybe yourself, maybe the guys standing 20 feet away who trusted you, created a constant low-grade tension that permeated every moment of operation. Veteran crews developed rituals, checking equipment in the same sequence every morning, using identical hand signals even when shouting might work, never joking about safety even in the bunkhouse. These weren't superstitions. They were coping mechanisms for men who understood, with brutal clarity, that their survival depended on maintaining absolute discipline in the presence of forces that could crush them without noticing. The steam donkey didn't just work in difficult terrain. It worked in terrain that had defeated every other solution, places where gravity, mud, and ancient forests conspired to make logging physically impossible by conventional means. Consider the Olympic Peninsula in Washington Territory, early 1890s. Slopes rising 40 to 60 degrees, covered in moss-slicked rock, and centuries of decomposing forest debris. Rain measured not in inches per year but in feet, upwards of 12 feet annually in some valleys. Douglas fir and Sitka spruce with root systems so massive that falling one tree could destabilize half an acre hillside. Ox teams took one look at the grades and refused to move. Horses broke legs in hidden root holes within hours of arriving. The timber was worth a fortune. Getting to it was supposed to be impossible. Steam donkeys made it routine. A typical high-grade logging show in the Cascades or Olympics ran like this. First, the donkey itself had to reach the site. Since the machine weighed 10 to 12 tons and sat on wooden skids with no suspension, moving it required either disassembling it into components, boiler, engine, drum, and hauling each piece separately, or using another donkey to winch it into position. On grades too steep for horses, crews would anchor a larger road donkey at the top of a ridge and cable haul the smaller, yarding donkey uphill, sometimes taking 2 or 3 days to move a quarter mile. Once positioned, the donkey became the center of a cable network that could extend over 1,500 feet in multiple directions. The key was the spar tree, a massive old-growth fir or spruce, 150 to 200 feet tall, that had been topped, stripped of branches, and rigged with steel cables running from its peak down to anchor stumps around the perimeter of the logging area. This created what riggers called a high lead system. Logs could be lifted partially off the ground and swung through the air over obstacles that would have stopped a ground-level drag cold. The physics were elegant in principle, terrifying in practice. A log weighing 25 tons, suspended 30 feet in the air by a cable under 40 tons of tension, swinging in an arc through standing timber at 10 miles per hour, represented kinetic energy sufficient to demolish anything it touched. If the log hit a standing tree, the impact could shatter the log, snap the cable, or pull the spar tree over. If the choker slipped, the log dropped like a bomb, and anyone beneath it had perhaps half a second to react. Not enough time to run, barely enough to register what was happening. Weather compounded every risk exponentially. Pacific Northwest rain wasn't a drizzle. It was a sustained assault that turned hillsides into rivers of mud. A steam donkey operating on a 50-degree slope in heavy rain sat on ground that could give way without warning, sliding downhill and taking the entire rigging setup with it. Operators learned to anchor the donkey itself with dead men, buried logs or stumps connected to machine with heavy chains. But even this wasn't foolproof. Local records from logging camps in Grays Harbor County describe at least 3 incidents where donkeys slid 100 feet or more during operations. Cable still under tension, logs still attached, the whole system transforming into a runaway mechanical avalanche. Cold weather introduced different nightmares. Ice formed on cables overnight, adding weight and changing their flexibility. A frozen cable pulled through a block could snap suddenly when the ice shattered, sending shards of steel wire and ice in all directions. Snow buried chokers, anchor stumps, and even entire logs waiting to be yarred, forcing crews to dig before they could work. Visibility dropped to near zero in heavy snowfall, making whistle signals the only communication method. But the whistle itself could freeze. Water vapor from the steam condensed in the valve and turned to ice, silencing the only voice between the donkey puncher and his crew. The most dangerous terrain wasn't the steepest or the wettest. It was the unstable ground where old logging slash, stumps, and root systems had been left to rot. This debris created what loggers called puncheons, hidden void beneath a surface layer of bark and moss where the ground could collapse under weight. A choker setter stepping onto what looked like solid earth could plunge 6 feet into a tangle of rotting wood and be pinned there unseen while the crew work around him. Period accounts mention several deaths attributed to puncheon collapses, and almost certainly more when unrecorded. The body simply listed as missing when crews moved to the next show. Yet for all the danger, the steam donkey proved itself in these conditions precisely because it was mechanical, not biological. Oxen died of exhaustion or injury and had to be replaced at enormous cost. Men could refuse to work in conditions they deemed suicidal, and many did, especially immigrant workers who hadn't been warned what they were signing up for. But a steam donkey, properly maintained and operated within its limits, worked in rain, snow, mud, and on slopes where standing upright was a challenge. It didn't care about comfort. It didn't quit. It converted firewood and water into pulling force, hour after hour, until the job was done or something broke. The steam donkey's impact on American industry wasn't gradual. It was a rupture, a sudden, irreversible shift in what was possible. Before 1880, Pacific Northwest logging was a regional cottage industry. Small operations cut accessible timber near rivers, floated logs downstream, and sold to local mills that served local markets. Production was constrained by transportation. You couldn't cut more timber than you could move, and moving timber by animal power had hard physical limits. The math was simple and unforgiving. After 1890, logging became industrial in scale and organization. Steam donkeys, combined with logging railroads and improved sawmill technology, transformed the equation. A single large operation in the Cascade foothills could now harvest 200 to 300 logs per day, compared to 30 or 40 per week just a decade earlier, and could access timber on slopes and in valleys that had been economically unreachable. This was an incremental improvement. It was a fundamental change in the industry's capacity. The numbers tell the story. In 1880, Washington Territory produced approximately 160 million board feet of lumber annually. By 1900, production had exploded to over 1.4 billion board feet, nearly a tenfold increase in 20 years. Oregon's production followed a similar trajectory, rising from 177 million board feet in 1880 to 1.1 billion by 1900. California, which had pioneered steam donkey technology, saw production jump from 300 million to 800 million board feet in the same period. This surge in timber production rippled through the entire economy. Cities like Seattle, Portland, Tacoma, and Eureka transformed from frontier outposts into industrial centers. Seattle's population grew from 3,500 in 1880 to over 80,000 by 1900, driven largely by timber money and the industries that fed off it: sawmills, shipyards, barrel makers, furniture manufacturers, and rail construction. Entire towns sprang up around logging operations. Company towns with a mill owner-controlled housing, stores, and often the local government. These weren't idyllic communities. They were extraction economies where wages were paid in company scrip, redeemable only at company stores at inflated prices, and where worker safety was an afterthought at best. The steam donkey made logging railroads economically viable, and logging railroads made the steam donkey exponentially more valuable. Before railroads, logs had to be moved to water, rivers, or coastal ports, which limited operations to specific geographic areas. With railroads, timber could be harvested anywhere a temporary rail line could be built, and steam donkeys excelled at the heavy pulling needed to load logs onto flat cars. A typical logging railroad operation worked like this. The donkey yard logs on the hillside to a central landing, where a loading boom, essentially a larger, stationary donkey with a tall mast, lifted logs onto rail cars. The loaded train ran downhill to the mill, returned empty, and the cycle repeated. On good days, a single railroad could move 50 to 100 carloads, each carrying 10 to 15 tons of timber, and do it profitably enough to justify building miles of track into previously inaccessible forest. The economic multiplier was staggering. Cheap, abundant lumber enabled the construction boom that defined the American West in the late 19th and early 20th centuries. Cities burned and were rebuilt in months. San Francisco after the 1906 earthquake, Seattle after the 1889 fire, because lumber was available in quantities that would have been unimaginable a generation earlier. The Transcontinental Railroad had opened western markets to eastern capital, but it was timber that provided the physical material to build the infrastructure those markets required: rail ties, telegraph poles, mine timbers, dock pilings, and millions of board feet of dimensional lumber for housing, commercial buildings, and warehouses. But the transformation wasn't just economic. It was ecological and demographic. Entire watersheds were clear-cut in years, not generations. Forests that stood for centuries disappeared, replaced by slash piles, eroded hillsides, and silted rivers. The speed of extraction outpaced any attempt at sustainable management, not because loggers were ignorant of the consequences, but because the economic incentives rewarded short-term volume over long-term stewardship. Steam donkeys enabled this extraction by making it possible to remove timber faster than it could regenerate, and to access forests so remote that natural regeneration would take decades even under ideal conditions. Compared to modern logging, the steam donkey era was both more and less efficient. Modern yarders, diesel-powered cable systems with computerized controls, hydraulic brakes, and radio communication, can handle larger loads more safely and with smaller crews. A modern tower yarder might be operated by 3 people doing the work that required 12 in the steam era. But modern machines are complex, expensive, and require infrastructure, roads, fuel supplies, specialized maintenance, that steam donkeys didn't. A steam donkey could be disassembled, hauled by horses into completely roadless terrain, reassembled in a day, and operated using fuel cut on site. This adaptability meant that steam donkeys continued working in marginal operations and remote locations long after diesel technology became available, not because they were better, but because they were simpler and more forgiving of improvisation. The steam donkey's reign lasted roughly 60 years, from Dahlbeer's first prototype in 1881 to the widespread adoption of diesel yarders in the 1940s. Its decline wasn't sudden, and it wasn't total, but it was inevitable. The first challenge came from the machines themselves. Steam donkeys, for all their power and reliability, required constant, skilled maintenance. Boilers had to be inspected for corrosion, cracks, and scale buildup. Fire tubes needed cleaning. Valves wore out and leaked. The friction brake, a simple band of steel or leather pressed against a drum, wore down rapidly under heavy use and had to be adjusted or replaced almost daily. A logging operation running 2 or 3 donkeys needed a full-time mechanic just to keep them operational, and even then, breakdowns were routine. Labor costs escalated through the early 20th century as workers organized and demanded better conditions. The Industrial Workers of the World, IWW, made significant inroads in Pacific Northwest logging camps during the 1910s, organizing strikes and slowdowns that forced operators to improve wages, housing, and safety standards. A steam donkey crew of 10 to 12 men represented a significant peril, and any technology that could reduce crew size while maintaining or increasing output had immediate appeal to cost-conscious operators. Safety regulations, virtually non-existent in the 1880s, began to emerge in the 1910s and 1920s as state governments responded to the appalling injury and death rates in logging camps. Washington state passed its first industrial safety laws in 1911, creating a regulatory framework that required basic safeguards: cable inspections, boiler certifications, and minimum crew training standards. These regulations didn't ban steam donkeys, but they made operating them more expensive and legally risky. An operator whose boiler exploded or whose cable killed a worker could now face fines, lawsuits, and even criminal charges, a significant change in the consequence-free environment of earlier decades. The technology itself was being surpassed. Internal combustion engines, gasoline and diesel, offered power-to-weight ratios that steam couldn't match. A diesel yarder could generate equivalent pulling force with half the weight, no water requirement, and number 30-minute startup time waiting for steam pressure to build. Diesel engines didn't need a fireman constantly feeding fuel. They didn't produce the massive clouds of smoke and sparks that made steam donkeys a forest fire hazard. And critically, they could be shut down and restarted instantly, eliminating the need to keep a machine running overnight just to avoid the time and fuel costs of a cold start. The economic argument became overwhelming during the Great Depression. Logging operations that survived the 1930s did so by cutting costs ruthlessly, and steam donkeys were expensive to operate. Fuel consumption, whether wood or coal, represented a significant ongoing cost. Water had to be hauled to the logging site, sometimes over miles of rough terrain. Maintenance parts, boiler tubes, valve assemblies, cable, had to be fabricated or purchased from specialized suppliers. A diesel yarder, by contrast, ran on fuel that was increasingly cheap and widely available, required less frequent maintenance, and could be serviced by mechanics trained on automotive equipment rather than specialized steam fitters. World War II accelerated the transition. The war effort demanded massive increases in timber production for military construction, ships, aircraft, and packaging materials. Operations that could mobilize quickly and produce efficiently received priority access to labor, fuel, and equipment. Diesel yarders, which could be manufactured faster and deployed with less specialized infrastructure, became the military's preferred technology. By 1945, most large logging operations in the Pacific Northwest had converted entirely to diesel, and steam donkeys were relegated to smaller, marginal shows or sold off as scrap metal for the war effort. But the end wasn't total. Through the 1950s and even into the 1960s, steam donkeys continued working in niche applications. Small operations in remote areas, where diesel fuel was hard to obtain or prohibitively expensive, kept running steam equipment because it could burn waste wood, slash, bark, and mill trimmings that had no other economic value. Some operators simply couldn't afford to replace equipment that still worked, even if it was obsolete. And a few old-timers, men who'd spent their entire careers around steam, refused to switch to diesel out of preference, pride, or sheer stubbornness. The last commercial steam donkey operation in the United States is believed to have shut down in the early 1970s, though documentation is sparse and likely incomplete. By then, the machines had become curiosities, relics of an earlier, more dangerous, and in some ways more impressive era of industrial engineering. What remains today are scattered fragments. Museums hold a few restored examples. Camp 18 near Seaside, Oregon, displays a 1920s-era Washington ironworks steam donkey. Collier Memorial State Park in southern Oregon has several steam logging machines, including donkeys and loaders. Private collectors own others, lovingly maintained or slowly rusting in barns and fields. And deep in the forests of Washington, Oregon, and Northern California, hikers occasionally stumble across the remains of old logging shows, rusted boilers, cable drums with broken teeth, wooden skids rotting into the forest floor, slowly being reclaimed by the trees they once helped cut down. The steam donkey's legacy isn't the machines themselves. It's the principle they embodied. Simple, robust technology applied with mechanical advantage can solve problems that seem impossible if you're willing to accept the risks and pay the costs. Modern logging equipment is safer, faster, and more efficient by every measurable standard. But it's also more complex, more fragile, and more dependent on infrastructure that didn't exist and wasn't needed when steam ruled the forest. 70 years. That's how long the steam donkey dominated American logging, from Dahlbeer's first prototype in 1881 to to the diesel transition completed by 1950. 7 decades of innovation, tragedy, profit, and transformation compressed into a chapter of industrial history that changed the physical landscape of an entire continent. The machine's technical legacy is straightforward. It proved that mechanical advantage, properly applied, could multiply human effort to scales previously achievable only through massive labor or animal power. Every modern cable yarding system, whether diesel, electric, or hydraulic, traces its lineage directly back to the principles Dalbier demonstrated in that first pull outside Eureka. The math hasn't changed. Pulleys and blocks still multiply force. Cables still work in tension, and gravity remains a primary force to be overcome when moving logs uphill. What changed was the power source, the control systems, and the safety margins. But the fundamental engineering? That was solved with steam, steel, and field experience over a century ago. The economic legacy is more complex and more troubling. The steam donkey enabled industrial-scale deforestation at a pace and scope that was ecologically catastrophic. Old-growth forests that had taken 500 to 1,000 years to mature were cut in 10 to 20 years. Entire watersheds were stripped, causing erosion, flooding, and the collapse of salmon runs that indigenous peoples had depended on for millennia. The timber built cities, railroads, and the infrastructure of modern America, but the cost was environmental damage that we're still trying to repair a century later. The steam donkey didn't cause this destruction. Human decisions about resource extraction did, but it was the enabling technology that made those decisions physically possible. The human cost is harder to quantify, but impossible to ignore. Thousands of men died in steam donkey operations. Some deaths were recorded. Coroner's reports, company logs, newspaper accounts, but many weren't. Immigrant workers, transient laborers, men with no families and no documentation simply disappeared. Their deaths noted only by the absence of a paycheck at week's end. The industry operated in an era before workers' compensation, before industrial safety laws, before the idea that employers had a moral or legal obligation to protect their workers from preventable harm. The steam donkey, for all its mechanical sophistication, was a killer because the systems around it, economic, legal, cultural, prioritized productivity over human life. Yet the men who operated these machines weren't victims, in the passive sense. They were skilled professionals who understood the risks and chose to take them, often because the alternative, subsistence farming, factory work, or urban poverty, seemed worse. A donkey puncher in 1910 could earn $5 to $7 per day, double or triple what an unskilled laborer made. That wage came with a trade-off. You might die. You'd almost certainly be injured eventually, and you'd work in conditions that destroyed your body over time. But for men with limited options, it was a choice they made consciously, and many took pride in their ability to master machines that terrified others. The cultural legacy is subtler but still visible. The steam donkey era created a mythology of masculine industrial competence. The idea that real men work with dangerous machines, understood mechanical systems intuitively, and solved problems through improvisation rather than by following manuals. This wasn't entirely myth. The best donkey punchers, riggers, and hook tenders did possess skills that border on artistry, developed through years of experience in conditions where mistakes were immediately and fatally obvious. But the mythology also obscured the reality. That this work broke men as often as it made them, that skill and caution didn't guarantee survival, and that the golden age of logging was built on a foundation of exploitation and environmental destruction. If this breakdown of historical engineering and its consequences gave you a different perspective on industrial progress, do us a favor. Hit subscribe and leave a comment sharing what you learned. What does your family's history intersect with industrial work like this? What machines or industries shape the place you're from? We're diving deep into the technology that built America, the real costs, the actual engineering, and the people who lived it. There's more coming. Comparing the steam donkey era to modern, logging reveals uncomfortable truths about progress. Yes, today's equipment is safer. Fatality rates in logging, while still among the highest of any industry, are a fraction of what they were in 1900. Yes, modern yarders are more efficient and less environmentally damaging per unit of timber extracted. Yes, regulations exist to protect workers and, to some extent, forests. But we've also lost something. the ability to improvise with limited resources, the understanding of mechanical advantage that came from working with simple systems where every force was visible and tangible, and the direct connection between physical work and measurable output. The steam donkey's final lesson isn't about the superiority of old technology. It isn't superior by most measures, but about the trade-offs inherent in technological change. We gain efficiency, safety, and scale. We lost simplicity, repairability, and a certain kind of mechanical literacy that was common when tools were simple enough to understand completely. Modern operators run machines they couldn't repair if they failed. Steam donkey crews ran machines they could rebuild from scrap if necessary, because understanding the machine's limits was a survival requirement, not an academic exercise. In the end, the steam donkey stands as a monument to an era when industrial technology was powerful enough to reshape landscapes, but simple enough that a reasonably intelligent person could understand, operate, and maintain it with hand tools and field experience. We won't return to that era, shouldn't return to it, given the human cost, but we can learn from it. The engineers who designed steam donkeys and the men who operated them understood force, leverage, and material limits with clarity that often exceeds what modern education provides. They couldn't calculate stress load with computer models, so they learned to read the signs of imminent failure, the vibration of a cable, the sound of a bearing, the smell of overheated metal, and react before catastrophe struck. That knowledge, practical, experiential, earned through risk and loss, is part of what we lost when we gained safety and efficiency. Whether the trade was worth it depends on who's answering. The engineer designing modern systems, or the ghosts of men buried under logs in unmarked graves on hillsides that are now second-growth forest. The steam donkey can't answer, but its legacy, written in steel and blood, and the stumps of forest that will never return to their original grandeur, asks the question for us. This script is for historical and educational purposes and does not replace modern engineering standards or professional guidance.